Greetings, everyone. We'll take a few minutes here to let folks join the webinar today. So just sit tight if you're already comfortably in the room, and we'll get started in just a minute. So, and while we're waiting, I just want you to know that we're really excited about the program that's coming together for our October conference in Providence, Rhode Island. So if you haven't yet, please stop by our IWCS.org website and see the latest information. And hopefully you're seeing the blasts and the information is coming across by email as well. So it's coming up quickly. I cannot believe we're already at the end of the summer. It just blows my mind. But anyway, so we'll just wait just another minute or so to let folks join. Yeah, we have an excellent audience today from all corners of the world, which is always nice. So we appreciate everyone for taking the time on a Friday and end your week with a real good, fine presentation that's really relevant in our industry these days. So just a minute more and we'll get started. All right, we can start the preamble. Folks will join if they're a little bit late, but welcome again to today's IWCS webinar. My name is Dave Cadu, and I'm honored to be your CEO and director of IWCS, and I'll be moderating today's webinar event. A few housekeeping items. As part of a larger audience, you will be in listen-only mode. So please note that. And this webinar is being recorded for rebroadcast both on our YouTube channel as well as the IWCS website. We encourage you to submit any questions that you have today during the presentation in writing in the chat function. The chat panel, once you click on the chat, should be on the right of your screen. And after typing in your questions in the space at the bottom, hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. So please enter that, and we'll ask those questions for you. Today, our webinar series event is being hosted by the Cable and Connectivity Industry Forum. And again, we're very excited about the conference, which is rapidly approaching in October. So again, these webinars help show the content that is presented at the conference. And this particular paper was presented last year in Orlando. So today we're honored and welcome Michael Dodds, who is a test engineer at Leviton in Pennsylvania, USA. And today Mike will be presenting on a very important topic as we evolve into smart communities, smart buildings, and the issues of extending the distance of network cabling infrastructure. And his paper is on the environmental resilience of twisted pair Ethernet applications at lengths greater than 100 meters. Michael has received his Master's of Science in Electrical Engineering and Biomedical Engineering from Drexel University. He is a test engineer, as I said, at Leviton's Systems Verification Lab in New Holland, Pennsylvania, USA. His work focuses primarily on extended length copper and fiber systems. Again, very, very topical as we go into the future of smart communities. So, Mike, again, thank you for contributing today, and we appreciate you presenting this to our wider global audience. Thanks.
Of course. Do you see my screen?
Yep.
Just want to make sure
Yes.
that's presenting properly.
Yes.
All right, then. All right, well, good morning, everybody. Like Dave was saying, extended length applications have become increasingly prevalent in our industry over the past few years. And it's a topic that I've written about multiple times in different capacities. A few years ago, actually, I wrote a paper on the viability of extended length applications. And then later, I wrote a paper on the quality of extended length applications. And now, kind of trying to cover all the basis of extended length and looking more into the environmental resilience and how well extended length applications can deal with real world stressors. So we were looking at multiple different cable designs, different environmental conditions, and basically just seeing how well these applications can hold up when they're underneath the stresses of the real world. So outside of a laboratory environment. All right, so we're going to start off with some basic characteristics of extended length applications and how they differ from your regular standards-based solutions. And then we'll delve into the questions that we hope to answer with our experiments. I'll explain how we investigated these questions, and then we'll delve into the results. And then finally, we'll get into the conclusions that we can derive from the results of our experiments. So one of the most important things to remember about extended length applications is that they're non-standard. So that means that there's no guarantee of interoperability that you would see with other standards compliant installations. So for example, you could connect a PoE switch to a outdoor PoE camera using an extended length channel. And initially everything could work fine. You could have perfect connection between your switch and your PoE device, but maybe you installed it in the winter, and then when it comes around to the summertime, things start to heat up, and you might be losing that connection between your PoE switch and your PoE device. So now you're essentially stuck with an application that only works when the weather's cool because it's a non-standard application. Or maybe you're trying to refresh the switches in your data center, so you swap out one compliant switch with another. Again, both switches are IEEE compliant. They're compliant to the application that you're trying to run, but the second switch maybe has a bit of a weaker PHY that it doesn't quite have the margins to its specification that the other one did. So now, because it's not sufficiently above the standard, your application no longer works. So essentially, you've dumped a couple $1,000 into equipment that doesn't work for your application. So in the near term, it seemed like a good investment, but now that you're actually trying to do some move, adds, and changes, things aren't working, and it can be a bit more of an investment down the road to fix that kind of situation. So again, that's the risk that you run with engineered solutions, is that the quality is somewhat uncertain. Again, PHYs, that is the chips within the switches and active equipment themselves, can be stressed by the additional length and also from the environmental conditions. And some might not actually be able to support the channels that the extended length channels that you're trying to install, while others do. Again, the quality between active equipment isn't constant. Some switches are better than others. Naturally, some switches are better at withstanding the stresses of the environment than others. And again, that's the risk that you run with these non-standard applications. So the additional attenuation and insertion loss that you incur from the extra length, as I said before, could be mitigated by some switches, but not by others. So if you have an initial switch that can handle the additional length of your extended length application, could be fine, but then you swap in another one that's still standards compliant, but doesn't quite have the transmission power capable of handling the additional length. So you just end up with an application that no longer works. Though it isn't as simple as just making sure the power coming out of your switch is high enough. Effectively, you want to make sure that the signal to noise ratio is good enough to maintain your application. It's not just all about power, it's all about the quality as well, making sure that your noise sources aren't overpowering your signal, which means that attenuation is really just one side of the equation. So as I mentioned before on the previous slide, ultimately there's two general categories of cable installations. So on one hand, you have your standards-based solutions, and these are developed in collaboration with industry experts, usually over the length of many years. They establish requirements for interoperability of different components of the system. It allows for easy moves, adds, and changes, and it can function as long as you have a minimally compliant component that you can substitute into that system. So think your 100-meter TIA standards channels, things of that nature. And then on the other side, you have your engineered solutions, and these are developed for very specific applications. So your interoperability is not guaranteed. Swapping out components, like I mentioned before, could result in a loss of functionality. And you may actually be relying on the performance margins of components within the system. So you're actually depending upon the components of the system performing better than standards compliance. So having additional margin above the minimum compliance for the standard for the application that you're trying to run. And obviously, the example of this that I'll be covering in this presentation today would be extended length applications, those being engineered solutions. So in this study, we aim to answer three main questions. Number one, how robust are extended length link segments in the presence of real-world stressors? Number two, do larger conductors and lower attenuation always translate to better extended distance performance? And number three, how can you be sure that an engineered extended length system will meet the needs of your installation? So we'll get into the test setup. So we conducted our analysis with 7 different cables, which I have listed in that table there on the right, ranked in order of attenuation. So cable number 1 being the one with the highest degree of attenuation, and cable number 7 being the one with the lowest. So obviously cable 1, you have a Cat 6, 23 gauge, and cable 7, you have a non-category compliant 21 gauge. So non-category compliant 21 gauge, obviously having the least amount of attenuation and the lowest insertion loss. Cat 6, 23 gauge of these cables having the highest insertion loss. And all these cables were verified to be free from manufacturing defects, so we wanted to make sure that there wasn't any outside effects affecting the results of our experiment. We didn't want faulty cable skewing our results. We looked at multiple different manufacturers, and some of these cables that we looked at actually were designed and could be targets for extended length applications. And these systems were tested as plug-to-plug direct attached link segments, so there wasn't any kind of jacks or patch cords or consolidation points incorporated into the channels under test. It was just straight one cable, one plug at each end, direct attach. And we started off at a length of all these at 200 meters, and we used the same cable samples and just gradually reduced their length as we tested various cable lengths under various environmental conditions throughout the test. So in terms of the active equipment that we used for our experiments, we used 6 different Ethernet switches, varying in ages, types, and manufacturers, just to get a sampling of the different kinds of active equipment out there in the real world. And as I'm going to show in the results of our experiment, is that you can see a lot of variation between the performance of switches and active equipment that you have out in the real world. Our sampling doesn't incorporate or doesn't encompass the entire variety of performance that you're going to see in the real world, but it does illustrate the point that you could have very good performance with one switch, but then you swap in the other one, and all of a sudden your application doesn't perform up to the standard that you need it to. And from these 6 switches, we looked at 5 different combinations that we used for testing, and all of these switches were verified to support standard length applications. So again, I mentioned we have those 6 different Ethernet switches that we used for our active testing, and using those 6 switches, we used 5 different combinations of switches. So we connected the link segments under test between those 6 different switches to make 5 different combinations. All right, in terms of how we actually transmitted the data, each link segment under test was loaded into an environmental chamber where it could be conditioned to a specific temperature. 5 meters of the near end and 5 meters of the far end were left outside of the environmental chamber just so they could reach the switches that I mentioned on the previous slide. And these switches were connected to a frame error rate tester using Cat6a patch cords and configured such that the data transmitted between the switches would be looped back to the frame error rate tester. So essentially, you would have a packet sent from one port of the frame error rate tester into a port on the switch, and using a virtual LAN or VLAN, that packet would be transmitted over the channel under test to the far end switch, and then again through a VLAN transmitted back to the frame error rate tester, so we could measure how well that frame is actually being transmitted between the switches themselves, because of the length of the Cat6a patch cords and the applications we're testing. You're not going to see any kind of errors occurring here. So any error that would occur in the transmission would be happening in this segment of the channel. So in terms of the data that we're sending in each of the tests, we conducted 1,000 base T gigabit frame error rate tests over these extended lengths between switches. And for each of the tests, 10 billion frames were transmitted bidirectionally, which took about 1 hour. And the characteristics of the frames are shown in that table there on the right. So basically, we had a pretty standard 64 byte frame for gigabit. Preamble size is pretty typical what you would see of an Ethernet packet. Frame size, payload, just for PDNA, so nothing really out of the ordinary there. And then in terms of the actual data link layer protocol, just Ethernet 2, network, IPv4, transport layer, UDP. It doesn't really affect the viability of the packet itself, but it helps us construct an actual packet that you might see in the real world. So this isn't some sort of special packet that we're sending between switches. So it represents sort of real world data. All right. And just as a side note, we chose to measure frame error rate, even though IEEE 802.3 specifies bit error rate, because you can effectively measure the bit error rate of gigabit within just a couple seconds or a couple minutes. It's very quick. And that doesn't really allow the active equipment to reach a steady state operating temperature. Effectively, the test will start, it'll end before the equipment can warm up or anything like that, or any of the adaptive equalization can happen within the switches themselves. So it's too quick. It doesn't really represent real world performance. And as another note, frame error rate is much more observable to the end user, because if you're looking at a bit error rate, if you drop, say, 100 bits over the span of an hour, depending upon where those bits are being aired or being dropped, you could end up with all 100 of those bit errors happening within one frame, in which case the user will notice just one frame being dropped. But if you drop, or if you air 100 bits and you have one bit in 100 different frames, then you're going to be dropping 100 frames. So we like to look at frame error rate just because it's more observable to the end user in terms of the overall quality of the transmission. And in terms of the temperatures that we tested these channels at, we looked at 30 degrees, 40, 50, and 60 degrees Celsius. And the lengths that we tested were 200, 180, and 160 meters plug to plug. And again, at each of these lengths, we tested the channels just to make sure that there wasn't any installation defects happening, so there wasn't any improper terminations that could skew the results of our testing. All right, now we'll get on to the results. So between all the samples, switches, lengths, and temperatures that we tested, we performed a total of 420 frame error rate tests. When we evaluated each sample across all the switch combinations, we can see that the average number of drop frames both increases as temperature and length also increases, which tends to make sense because if your signal to noise ratio is staying the same for a specific cable, as you're increasing the amount of attenuation, your signal component of signal to noise is going down. So ultimately, you're going to have more errors occurring because your signal to noise ratio is getting worse. And that's the trend that we see. And for each of the cables, the average number of drop frames at 30 and 60C decrease as we reduce the overall length of the link segment. So like I said before, Signal to noise ratio ultimately determines how well your data is going to be transmitted within your system. And if you're increasing the temperature, your attenuation is going to be going up and your signal power is going to be going down. Hence, your signal to noise ratio is going to be getting worse. And at each of the lengths, the average number of drop frames increased or stayed the same when increasing the temperature from 30 to 60. All right, if we look at the results more granularly, we can see a pretty significant variation in link performance based on the switch combination used. So if you just look at, just say, for example, sample number one right here, if you look at the performance of one of the switch combinations, so basically what this chart is shown right here is the results for each of the cable samples that we tested, their performance with each individual switch combination. This first chart here is at 200 meters, 30 degrees Celsius. So if we look at number one, you're dropping somewhere in the realm of 2 times 10 to the 9th frames with one switch combinations. But then if you look at another one, you have basically 3 orders of magnitude lower in terms of your number of frames being dropped. So there's a pretty significant variation there in terms of the quality. And those differences can be even greater for some samples under test. So cable number 5, you're seeing basically a 5 order of magnitude difference in terms of the number of drop frames. And that kind of relationship maintains as you change the temperature at a given length. So as you can see, for the at 200 meters, we start at 30 C and gradually increase the temperature. The amount of drop frames basically increases for every single one of the cables under test. And then we see a pretty similar trend at 180 meters. So again, you see that significant variation between switch combinations, and the average number of drop frames increases with temperature. So if we look at the results here, at 30 C for 180 meters, as we increase the temperature to 40 C, then to 50 C, and then to 60 C, again, we see all those number of drop frames increasing. But what we do also see relative to the 200 meter testing is that overall, the number of drop frames is lower across the temperatures. So say at 200 meters with 60 C, the number of drop frames is a lot higher than, say, for 180 meters at 60 degrees C. And then again, we notice the same trend with 160 meters that we noticed with 180 and 200 meters. And I think one thing that's interesting to note here is the increase in the number of drop frames for table 1. So switch combination A produced less than 100 frame errors at 30 C, but more than 1 billion at 60 C, which I'll show here in a little bit. And basically at 60 C, cable 1 produced less than 10 frame errors with switch combination E. So basically this just highlights the effect that temperature and equipment choice can have on extended length applications. So this is a pretty good example of you having an installation that might work to the quality that you want it to when you install it at a pretty typical elevated temperature, just a little bit above room temperature at 30 C. But then as you gradually increase the amount of temperature, so again, we're looking at cable 1 here, not a whole lot of frames being dropped here with that switch combination A, but then as we increase the temperature just a little bit, you're jumping all the way up to 10 to the 9th frames being dropped. So just illustrating the pretty significant effect that the environment can have on your transmission quality. All right, and the graphs on this slide show the relationship between the average number of drop frames for each cable sample across all switch combinations and each cable's margin to 1000 base T insertion loss spec. So we see at 200 meters, you have some very lossy connections, and there's many instances in which link can't be established. And then we look at 180 meters, it's still lossy, but the frame errors generally decrease, and there's still a few instances in which link can't be established across the samples that we tested. But again, as we cut down from 200 meters, where almost all the links are incredibly lossy, and then we cut back 20 meters to 180, we're having some samples even down as low as less than 10 frames being dropped. So again, just showing how much your performance can change just over a few over a 20-meter decrease in length, or a decrease in the amount of attenuation you have. And then at 160 meters, link can be established with each of the cables, but again, a lot of the connections are still lossy, especially once you get to those elevated temperatures. So 60 C, again, we have some cable samples which were completely fine at 30 degrees Celsius, but then once we cranked up the temperature to 60 C, started dropping in the realm of almost 1 billion frames over the duration of 1 hour. But overall, there isn't a very strong correlation between insertion loss margin and the average number of drop frames within each of these lengths. So if we look at 200 meters on your y-axis, again, we have the average number of drop frames, and then we have the margin to the 1000 base T insertion loss spec. You're not really getting much better performance by lowering your attenuation than you would if your attenuation was higher out at these lengths. So it's all kind of at the same level, very lossy connections, despite how close you are to the 1000 base T spec. And again, at 180, it's a bit of a mishmash where you have samples with higher attenuation doing better than samples with lower attenuation, and then vice versa. So not really a strong correlation there. And then again, at 160 meters, you have everything basically falling at the same level of average frames being dropped, regardless of the attenuation. So what can we conclude from all this testing that we did? So if we look back at the questions that we asked at the beginning of the presentation, number one is how robust are extended length link segments in the presence of real world stressors? And I think the results of this show that transmitting 1000 base T at lengths greater than 100 meters is increasingly likely to result in packet loss as length and temperature increase. So basically, the longer you get beyond 100 meters, the higher likelihood that you're going to see a significant amount of frames being dropped. And even more so, if the ambient temperature of your installation could increase over time, you could see a pretty significant increase in the amount of frames being dropped as that temperature increases as well. So the second question we asked, do larger conductors and lower attenuation always translate to better extended distance performance? And I think the results of this say no. And as with all forms of digital communication, you need to maintain an adequate signal to noise ratio. And like I said before, attenuation is only part of the SNR equation. So it's not like there's any real magic bullet in terms of making extended length applications work. So you could basically with cable design, sell out and make your attenuation as low as possible. But if you're not taking the proper design choices to mitigate the noise that can be incurred from having, say, larger conductors and lower attenuation, then you're not really going to be accomplishing a quality extended length system. And lastly, I think probably most importantly, is how can you be sure that an engineered extended length system will meet the needs of your installation? I think it's very important to ask manufacturers how they're actually verifying their extended length systems. So if a manufacturer is saying that they'll support a specific application out to a specific length, I think it's important to make sure that they're accounting for real world variability. And also, I think it's important to specifically ask what they're guaranteeing. Are they guaranteeing that the installation is going to support error-free transmission for over the span of so many hours, or are they basically just saying that at room temperature, under the influence of no environmental stressors, you'll still have a very, very lossy connection, but it will link up. So I think it's very important to kind of get some clarity on what is being guaranteed, how it's being tested, because these are non-standard applications, so there isn't really any specific expectation of quality. All right, and then to recap, transmitting 1000 base T at lengths greater than 100 meters is increasingly likely to result in packet loss as your temperature and length increases. So with a given cable, if you are more likely to produce more drop frames as temperature and length increases. Again, extended length systems are engineered solutions. They're not standards-based solutions. So there's no guarantee that swapping out compliant components with other components will result in the same performance. And then when specifying twisted pair copper systems beyond 100 meters, it is important to understand how manufacturers actually verify their product's performance. So are they doing their due diligence and accounting for the variability that you would see in the real world? Are they accounting for the stresses that you could see in the real world? Or are they just basically connecting two random pieces of equipment, testing it once, and then saying everything is good? So knowing how a manufacturer actually verifies their claims can help you make wise design choices down the road and robustly mitigate real-world stressors instead of basically making a system that's penny wise and pound foolish, because you could be saving a couple bucks at the initial stage where you're effectively lowering the amount of TRs that you need by using extended length applications. But then those systems end up not working once environmental stressors get introduced, once temperature increases, and now all of a sudden you have a bunch of dead links and you're swapping out equipment, you're completely restructuring the topology of your network just because it was more convenient in the short term to use extended length applications, not knowing if those applications would hold up under the stresses of the real world. So again, just to sort of wrap everything up, systems that extend beyond 100 meters can simplify installations and reduce both cost and labor in the short term. But as I said, and as I've kind of been warning throughout this entire presentation, if those systems operate at the limits of what your specific network equipment can support, then the cost of maintenance could outweigh the cost of maintenance in the long term could outweigh the savings that you make in that short term. So you need to be very aware of all different facets of the installation. So with that, I thank you all for your time and attention, and I'll turn it over to some Q&A.
Fantastic, Mike. Yeah, thank you so much, Mike. Very practical and informative testing and evaluations for these increasing and emerging capabilities of the network. And I guess the first question is, as extended distance go out to devices like cameras and control systems and things like that, they're typically both powered and data. And it's not only, 100 megabits or gigabit requirements, it may be much less than that. Did you account for any powering scenarios and what the impacts might be on the environmental and temperature impacts when you're using powered or energized PoE network cabling scenarios?
Yeah, that's part of what we're trying to account for when we elevated things up to 60C, because your ambient temperature, if I mean, I don't know where people would specifically be installing it, but if the ambient temperatures get up to 60C, that's pretty high. But there's also the heat rise that can come from PoE. So if you had a lot of cables within a close density that aren't necessarily good at dissipating heat from PoE rise, you could have a hot ambient temperature and temperature rise from PoE such that the cable temperature itself could be elevated up to 60C. So that's kind of what we were evaluating when we tested these all the way up to 60C. Like I said, an ambient temperature of 60C would be relatively high, but it's not out of the realm of reason if you incorporate that temperature rise from PoE. So in a way, we did evaluate that.
Yeah. Again, I want to remind the audience that if you have any questions for Mike, please enter those questions in the chat. We do have time for a few more questions here. So I guess it's fair to say, Mike, that based on actually how much data rates you need for a particular extended distance device and the limited amount of power that you might need, you could probably have a better success ratio or less loss at those lower requirements. Is that a fair statement or no?
Are you asking if it's a higher probability of success at the you're saying
At,
at the like shorter lengths above 100 meters?
well, at shorter or lower amounts of data required,
Hmm.
data rates or power. You know, less power, less data, the less loss. Is that an inaccurate correlation?
No, I think it's a fair assessment. We only looked at gigabit for this testing,
Right.
but again, if you look at the specific bandwidth being used for say like 10 base T and 100 base TX, it's not as high as what you would see with gigabit, and because of that, your the overall attenuation of like the frequency range that you're using for that data transmission, uh, it's not going to attenuate as much because again, you're not using as high of frequencies. So you could have more success, yeah, with a like a 10 base T or 100 base
Right.
TX. But yeah, again, we didn't evaluate that, but I think that's a pretty fair assessment.
Good. Did you have any trouble connecting to the larger conductors with your field term plug?
We didn't. We would use a plug that was able to accommodate the different conductor sizes that we use for the experiments. They are out there, but again, they're not. You're not really going to find a whole lot of crimp-on plugs that are able to take in like a 21 gauge cable. So we would use basically reusable field terminated plugs.
Yeah. Um, and a testing procedure question within the chamber. Were you able to guard against interwinding crosstalk between the cable wraps while it was in the chamber?
That we didn't look so we basically put everything onto reels in environmental chambers. So we had kind of a um, standard form that the cables would be tested in. For gigabit, we're not all that concerned about noise being transmitted between like a cable running next to itself. If we were testing something like 2.5G or 5G or 10G, I would be a little bit more concerned about that. But again, just because of the frequency range that gigabit uses, it we've never really seen that being an issue of like noise bleed over of a
Right.
cable kind of being wrapped in on itself. Again, yeah, with
Yeah.
higher data rates, I think absolutely it would be something we'd have to mitigate. But for 1,000 base T, it wasn't a concern.
Good. Yeah. Um, when terminating, were the field term plugs reused?
They were, yeah. Yep. Same
Okay.
plugs were used at each stage at each length.
Alrighty. And did you happen to perform a control experiment, perhaps using standard 100-meter links for your reference?
Yep. Yeah, the switches that we use for our testing are part of a switch bed that we've been using pretty consistently. But as a control, we did look at basically minimally compliant Cat5e channels and verified that gigabit transmission was error-free between each of the switch combinations.
Yeah. And then you extended the testing out to the further distances in the
Yep.
200 meters and is what was the maximum distance that you actually looked at? Was it the 200 meters?
Yeah. For this testing, 200 meters was the maximum length that we looked at.
Right. Okay. Let's see. Did you determine what was the main contributor to the error rates outside of IL?
Uh, we didn't. We weren't able to determine specifically what what levers to pull in terms of cable design in order to make sure that in order to improve the frame error rate at extended lengths. But again, it all boils down to the signal to noise ratio of what's being transmitted over the cable itself, and attenuation is just part of that. I mean, there's also components of um, basically how is the active equipment processing the symbols that are being transmitted over your link segment. So they play a role in it as well. Um, and in terms of different noise sources are filtered out and canceled and whatnot by the active equipment. So there's certainly ones that can be sort of optimized, I guess, for an application. But again, you're kind of designing it specifically for a an Ethernet port that's going to filter out noise in a very specific way. So just kind of thinking as an example, you could design a cable to mitigate crosstalk, or rather, yeah, mitigate crosstalk as much as possible because you don't think it's going to be canceled out as much by the Ethernet ports at both sides of the system, while leaving another noise source unoptimized. You could have success with an Ethernet port that cancels out all those other noises, or you could have another Ethernet port that basically cancels out crosstalk, which you've already optimized, and you're not really going to see a whole lot better of a performance there. And those other noise sources are all of a sudden going to degrade your signal integrity. So, like I said, it's very specific to the kind of active equipment that you're using, because there's digital signal processing that's happening that also affects the frame error rate of the system.
Okay, I think you may have mentioned this already, but are you planning to perform any 10 or 100 megabits per second testing?
We have in the past. We just haven't put it into a paper. But yeah, we have looked at that in the past.
Okay, and I think this is a comment or just a follow-on question. Did you use the same exact plugs, or meaning reusing plugs? That's just an observation.
Yep, same exact plugs.
Very good.
And yeah, and they were
Yep.
brand new plugs for each of them, so there weren't any. We're trying to make sure that there wasn't any issues of, say, the tines on the field terminated plugs that would say if they were used plugs that were used for a larger gauge cable before. There could be some issues if you try to use that with a say a plug's been used with a 21 gauge cable before, and then you reuse it with a 23 gauge. You could have some issues there. But we used brand new plugs for each cable, so that wasn't a concern.
All right. We got a few acronyms here, but you're probably familiar with them. Switches employ PHYs with elaborate register functions that can be pulled to identify the SNR or the pH of the PHY. Were you able to get down to the register addressing level of the PHY to determine what a typical SNR for the compliance switch would be? Maybe this is a next paper discussion, but I trust you understood all of that.
Yeah. Oh yeah. We couldn't do that yet, but that is something that we're looking to do in the somewhat near term, is actually get down to the phi level to determine what the actual process signal to noise ratio is, because like I mentioned before, that the phis themselves are processing and cleaning up the signal to a certain degree, and each switch is going to do that differently. But yeah, in order that would give us a very clear idea of, is this specific port compliant? Is it meeting all of the active equipment requirements for 1000 base T or for 10 base T? But yeah, we didn't look at that yet. We're building towards getting that capability.
Fantastic. Well, we appreciate all the questions that came in from the audience. We understand that it is a vacation period, a heavily vacation period around the world. So we appreciate your time to come join us today. And again, Mike, thank you so much for the engaging conversation and really good information here. Please note the contact points being shown here now. Should you wish to contact Mike after today's event. Again, this webinar has been recorded. If you have colleagues that are in fact on vacation or wherever they are, and remind them that you can view this webinar again on either our YouTube channel or our website. It typically takes about a week or so to get it cleaned up and put on. So also the papers will be, we're in the process of updating all of the archives and information from last year's conference. So this paper will be on the archives here again shortly. So you'll be able to reach out and get the written paper as well. For the IWCS webinar series, we conduct typically a technical paper presentation once a month, typically the third Friday of the month. And we also do, on occasion, some sponsored company events as well for supplier spotlights. Our next scheduled technical paper presentation will be on Friday, September 20th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for these events, so please feel free to share those announcements with your colleagues so that they can join in and register as well. It's very important that we all recognize and appreciate the strong support and contributions to the success of our Cable and Connectivity Industry Forum from our partner level sponsors. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and to our global community. So again, thank you to these leading suppliers in our industry for your support. And I want to make sure that you're well aware that registration is now open. Our program is rapidly coming into full view and focus. So please stay tuned to our website to see the latest uh, program. And we hope that you'll save a few dollars and register here in the early bird session until about mid-September. You've got an opportunity to save some money on the registration. But just so many really engaging opportunities. A lot of content. Our plenary speaker and some special sessions on the smart grid, which of course extended distance is an important component of that. And so there's a lot of compelling information that you will receive. But most importantly is the networking, is seeing your colleagues from around the world and be able to talk and communicate with them both within the sessions and also in some of the social opportunities as well. So we hope that you will register and participate in Providence. It's typically a very well-attended conference when we're in New England in October. So look forward to having you with us. And again, for over 72 years, we've been presenting the Cable and Connectivity Industry Forum, and it is from October 14th to the 17th at the Rhode Island Convention Center. And the hotel information, everything is easily findable on our website. So please stay tuned to your inbox, your social media, and our website, of course, as information continues to be placed out there. So again, good evening, good afternoon, good morning, wherever you are. We really appreciate you being a part of us, and everyone have a great weekend. And Michael, thank you so very much.
Of course.